Now that we have established formulas for the sine of a sum, sine of a difference, tangent of a sum, and tangent of a difference, we can utilize those formulas to find trig values of angles that we're not quite as familiar with as some other angles. We're very familiar, or hopefully at this point, very familiar with trig values for multiples of 30 degree and 45 degree angles, right? Your 30, 60, 90s and so forth, or your 45, 90, 135s and so forth. But something like 165, the tangent of 165 is not a very common angle or something that we've seen very often, right? We could obviously punch it into a calculator, but that doesn't give us an exact value. It gives us a decimal approximation. It's still rounded off, to 9 decimal places or 8, whatever your calculator is programmed for. And so what we want to do is be able to get an exact form with roots or whatever the case may be, square roots, whatever, for things like the tangent of 165. And so to start this off, we're going to be utilizing the sum of angles that we're familiar with or the difference of angles that we're familiar with. Again, we're familiar with the multiples of 30 and the multiples of 45. And so as I look at this, I think, well, what can I add to get 165? Or what can I subtract to get 165? And I think with 165 being a little bit bigger angle, adding is probably the best way to go. And I think about 165, well, let's run through some numbers. 100 plus 65, but I don't know either of those very well. It's 145 and 20, it's 140 and 25. But none of those angles really work out well. So if you're thinking of multiples of 30, multiples of 45 that would add up, well, how about 120? 120 plus 45 would work. 120 is a multiple of 30, 45 is a multiple of 45. So those two would work. Let's try that to start out. And if it doesn't work well, we can always change it up. So we'll call this the tangent of 120 plus 45. Right? Because 120 and 45 makes 165. Okay, so now if 120 is like the A in our formula and 45 is like the B in our formula, then we can just start plugging stuff in, right? So the tangent of A plus B is found using this formula. We can use the tangent of A, which is our 120, plus the tangent of B, which is our 45, over 1 minus the tangent of A, which is 120, times the tangent of B, which is 45. Okay, so we're just filling in the A's as 120 and the B's as 45. Okay, so now I need to actually find the values for each of those angles separately. Now we can do that. The 45 we can do pretty easily. You guys probably know this one already, but I'm going to run through it anyway with a special triangle. The special triangle for 45, right? 45, 45, 90. The tangent of a 45 degree angle, opposite over adjacent, is 1. Okay, so the tangent of 45, I'll just write that up here for a moment, is equal to 1. Okay, we can also find the tangent of a 120 degree angle. Maybe not using we can utilize a special triangle in a moment. We know that the 30, 60, 90 triangle has side lengths of 1, 2, and root 3. But 120 isn't on this triangle. 120 is in the second quadrant. And it is 60 degrees back from 180, right? And so in that second quadrant, if you think about a right triangle, the horizontal leg would be -1 because it's going left for an x value. The height would be a root 3 and the hypotenuse is 2. We don't care about the hypotenuse for a tangent. So tangent is opposite over adjacent, or y over x, and that's going to be root 3 over -1 or just negative root 3. So the tangent of 120 is negative square root 3. So with these two values, I just gotta plug them into the formula here and maybe do some simplifying to make it look nice if necessary. So I've got tangent of 120 is negative root 3 plus the tangent of 45, which is 1, all over 1 minus this stuff. Well, tangent of 120 is a negative root 3, and the tangent of 45 is 1. I could just clean this up a little bit. Just maybe writing the numerator as 1 minus the square root of 3. And writing the denominator, well, clean up the double negative here. It's 1 plus the square root of 3. Okay, not bad. However, 1 minus root 3, 1 plus root 3, that's an exact value, and it is accurate. However, we've talked about this before, we always want to rationalize denominators, okay? In the past, we've mostly done rationalizing denominators when there was a single term on the bottom, but here we have 2 terms on the bottom. Now, how do we rationalize a denominator with 2 terms? Well, there's a trick in mathematics, you may have seen it in an algebra course before, where you multiply by the conjugate of the denominator. Remember, a conjugate, I think we've talked about this in the past, but if not, I'll bring it up now. The conjugate is the same 2 terms, but with a different sign. So 1 plus root 3 has a conjugate of 1 minus root 3. And if I multiply that on the bottom, I have to do the same to the top. So I get 1 minus root 3 on top. Now we need to distribute, simplify a little bit further. Rationalizing a denominator is going to be important. I believe my math lab assignments are going to require you to do this. So you're going to want to make sure to be careful to rationalize things. So 1 minus root 3 times 1 minus root 3. If I distribute that through, on top, 1 times 1 is 1. 1 times negative root 3 and 1 times negative root 3 is added, negative root 3 and negative root 3 makes 2 times negative root 3. So it'd be minus 2 root 3. I'm gonna keep from multiplying or showing all the steps there, but you're just doing the, for lack of a better term, the FOIL method, right? And that's the O and the I combined in FOIL. And then the root 3 and root 3, the double negative makes a plus. A root times itself is squaring it, so the root disappears, you just get 3, right? Root 3 times root 3 is 3. And then on the bottom, when you multiply by 2 conjugates, you get the difference of the squares. Okay, so you get the square of the first minus the square of the second. If you multiply all that out using, again, the FOIL idea, the O and the I cancel out, and you just are left with the F and the L subtracted. And so you end up with 1 minus, so the square of 1 is 1, the square of root 3 is 3, so it's 1 minus 3 on the bottom. And then we can go through and simplify further. 1 and 3 makes 4 on top, so it's 4 minus 2 root 3, all over negative 2. Wow, this simplifies even further. This is a really nice one. I could divide this negative 2 to both terms on top. So 4 over negative 2 is negative 2. And, well, actually, maybe I'll write that out just so you can see how it splits up. I'm getting too carried away here. It's 4 over negative 2. And then we've got a minus 2 root 3 over negative 2. If I really wanted to split that apart. I can then reduce each fraction. So the 4 over negative 2 is negative 2. Double negative makes for a plus. The 2's cancel here, I just get a root 3. So it's really negative 2 plus root 3. Now I can verify that, okay, on a calculator, just to get you an idea that that's not just me making stuff up, right? The tangent of 165, well, 165 is a second degree angle, second quadrant angle, right? 165 is over in the second quadrant. It's not quite down to 180, but it's bigger than 90. So it's a second degree angle, which means it should be negative, okay? What you'll find is that 2 is bigger than root 3, so the negative will dominate here. This value will be negative. If I throw this in a calculator, which I need to grab, okay, got my calculator. I'll display this once I punch it in. Negative 2 plus square root of 3. And while I'm at it, I'll throw in the tangent of 165 and make sure that I'm in degree mode, which I'm not. There. And you'll find, hopefully you can see that, it'll focus, the two decimal expansions are the same, and they're both negative, which makes sense because I said it should be, the 165 is in the second quadrant, and tangent is negative in the second quadrant, okay? So, that worked out nicely. It does verify that those are the same. Again, this is with the denominator rationalized. Obviously, negative 2 plus root 3 is a much nicer expression than 1 minus root 3 over 1 plus root 3. Okay, so this is what we'd be looking for in this as an answer, is this simplified version with the denominator rationalized.